right, so here we go. Finally, moving on to the next unit. And what we get to talk about with circular motion is what happens when the force is perpendicular to the velocity. That right there is the key to the entire unit. Because everything we've studied so far, the forces have either been in the direction of motion or against the direction of motion. When we look at the sum of the forces causes the mass to accelerate. But what happens if the force is perpendicular to the velocity? Yeah, you guessed it. It's in the title. The object goes in a circle. So what I'd like to do is to just show you a couple simple demonstrations. I think in a previous video, I likely would have gone through some of these notes already. Here we have most of our formulas in our diagram for the unit. Even talked about the 5 things that can cause an object to go in a circle. Now, all of these forces, except for magnetism at the end, can cause an object not to go in a circle. But if the sum of the forces is perpendicular to the velocity, that object will go in a circle. So when it comes to circular motion here, I got the easiest demo I can do. I've got a string attached to a mass that I'm going to spin in a circle. It's a little tight over here. There we go. Now, you can see that the string is applying a force. Now, this is a vertical circle, which we'll get to in a couple days. So I'm going to shift the plane so that it's a horizontal circle here. But it doesn't make for very good videos. So let's take a look at it vertically. Realize, though, we're talking about a horizontal circle right now. Now, oh, damn. Good. Let's try that again. One more try. I think I got it this time. It's I look much, damn it, slower than I am. But here's the thing. If we freeze the mass right here, what's the direction that the string is applying a force on the mass? Yeah, exactly. It's applying a force towards the center, or a centripetal force. Now the velocity at that moment is a tangential velocity. Sometimes we also call it a linear velocity, but I think when we start off calling it a tangential velocity makes sense because it's to the circle, to this tangent to the circle. And you guys have learned tangent to the circle means that at this moment right here, it would be going straight up. So if I have enough talent, questionable, to let go of the string at exactly that moment, which way is the mass going to go? That's right. Almost exactly straight up. Because the velocity is tangent to the circle. And that's true anywhere on its path. Here, 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 here. The velocity is always tangent to the circle. Hence, tangential velocity. So it's pretty easy with a string. Here, I have an Aboriginal bull roarer. My friend Dino Sabato, who I went to college with, brought it back from Australia. Beautiful, hand-painted by some Aborigines. And then somebody stole it. I lost it somewhere along the way. So instead, I've had to replace my beautiful hand-painted bull roarer with a ruler. But we can still get the same effect. Now, you guys likely have not seen the movie Crocodile Dundee 2. You probably shouldn't have. Do you hear that? Do you see what's going on? Now, apparently, Aborigines in Australia used to use this to communicate over long distances. Whether that's 100% accurate, I don't know. But I do know that the string is applying a force tangent to the circle. The sound is coming from the ruler actually, bull roar, rotating as it goes. Did you notice? I bet you did, that it actually has 2 different modes too. Ah, broke it. Damn it. Now let's try that again. It has 2 different modes. One when it's spinning in one direction, and one when it's rotating around its axis in the other direction. Tension. It can make things go in a circle. A quick demo, and that is how friction can cause an object to travel in a circle. Now, what you see here is a ball that's attached to a rod. It's all glued down. That's actually for a different demonstration. What I'd like to show you instead is what happens if we place a coin. That's actually a Nobel Prize gold coin on the rotating platform. And you can see it stays on the track. How does it do that? Well, there's a force of friction towards the center as it rotates, because an object in linear motion wants to stay in linear motion, or an object at rest will stay at rest until acted upon by an outside force. So the fact that it's going in a circle means there must be a force acting on it. And that force is the force of friction. In this case, it's static friction because it's not moving. Now, if I replace that coin with a mass, the coefficient of static friction is still great enough that it doesn't go flying off. Whoop. If I speed this up to 78 RPMs, we can see that the coefficient of static friction is still great enough that those coins stay traveling in a circle. Now, the force, at every moment, the force of friction is towards the center of that rotating platform. So, what happens if we put it on a platform that doesn't have a constant rate or a constant frequency? Well, if I place my two objects down, now this is a really nice frictionless table. It's frictionless, the ball bearings are, not the surface. So if I spin it at a fairly slow rate, not that different than the record player, I can see that they both still stay at rest. Static friction is acting on it. But as it speeds up, that happened kind of quick. What happened to that outside chocolate coin? That's right, it fell. You know, it's hard to be your own cameraman and production and voice talent. So let's give this a kick. Now, static friction is causing it to travel in a circle, but it speeds up a little bit more, and a little bit more, and a little bit more. And eventually it's going to get to a point where it overcomes the static friction. Oh, and when it does that, which way did it fly off? That's right, tangent to the circle. Now, I got another one. And this is a grade school demo, so I feel a little silly doing it, but you know, they pay me, so I can give it a try. Hopefully, don't run into any issues. I got a piece of plastic with 3 strings attached, and I'm going to place a plastic cup on there. And right now, what can you tell me about the system? Yeah, that's right. It's at equilibrium. Nice job. All of the forces are balanced. We have the force of gravity down, and we have the normal force up. Good. Now, if I move this sideways, what force prevented the cup from just staying at rest? Because the cup did move, didn't it? See? So since the cup moved here initially, there must have been some friction acting on it. Good. All right. Now, if I get this thing spinning at a rate that's fast enough, I should be able to get it to travel in a circle. That didn't work. Any ideas why? Yeah, because I didn't fill it up with water like your 3rd grade teacher did. You know how much smarter your 3rd grade teacher is than I am, don't you? You do realize that, and they're saints. But I knew that was going to happen. What do I need to increase about the cup in order to have it travel in the circle? Yeah, that's right. I need to increase its weight. That would increase the normal force, which would increase the it would increase the force of friction. Coefficient of friction stays the same. Now, sort of counterintuitively, the more massive it is, the more likely it is to be able to go in that perfect circle. So if I get it spinning And are you ready? Vroom. Now, I know you're not all that impressed. I did go to physics teaching school, and this was like in the first week. We all stood up, we did this. You passed this, you could move on to the next unit. At each point, the plexiglass is actually applying a normal force, pushing inwards, causing a centripetal force. The string has a tension in it. That's applying a centripetal force to the plastic. And there's also friction between the cup and the plastic surface that's also, in its way, allowing it to go in a circle. I know that you're not that impressed. I know. YouTube spoils everything for us physics teachers. So I might as well try something different. It's a little tight. I haven't done this on video before. We'll see how this goes. But I think I like it because this is more dangerous. I haven't done it in such tight quarters. But if I get it going fast enough, I can get this to balance and continue in a circle. Even though the normal force is pushing in, it's traveling in a circle, what force is pulling down on the cup? That's right, gravity. What force is keeping the cup from sliding downwards? Yeah, that's right, friction. So it's actually friction that allows this cup to stay still. Now, I've got this going pretty well. How's it gonna go when I stop? 50-50. Luckily, there's nobody here. Circular motion. Piece of cake.